lecture.
Seriously, personal lecture.
Pretend you're making eye contact with other people in the room.
So yeah, so we're going to continue on the topic that we were discussing before. Actually, let me just make sure we're not. Okay, so there's some reading, and hopefully, did you find the midterm okay? It's in the assignments, even though it didn't send out an email to everyone. If you go into the assignments on Lima, you'll see the midterms there, and it's a due week from Friday.
Yeah, you mentioned that last class. I didn't look at it yet.
Okay. Well, I highly recommend people look at it just in case they have questions about it, right? But whatever. Okay. Check it out. I don't think it'd be too bad. So I think we kind of buttoned this topic up last time. I was going to ask if you had questions about that thing with the time scale. I mean, it's kind of a statistical argument about looking at the amount of radioactivity that we find in the very early solar system materials and then kind of backtracking to when we think that was formed, either by a single event that made those isotopes, which could have happened in our sun, right? Or a whole bunch of events. And the whole bunch of events method gives us that like 15 billion year estimate. So, I mean, it's probably true that the number density of large scale events has, large stars that are going through S process and R process has probably decreased over time because you got more massive stars earlier on when stuff was still extinct. And people have tried to incorporate these things as well into the discussion, but ultimately it's really kind of a rough estimate, right? It's probably not even good to a few tenths or maybe even a billion years. It's in the pocket with a lot of the physical estimates that people make. So that's why people kind of use it. So it seems like multiple lines of evidence tell us the universe is about 15 billion years old, and our planet, represents something less than the last third of that. So what we're going to talk about today is the stuff that happened once our what's called solar nebula, which is not yet our solar system, but it's the cloud of gas and dust that our solar system is going to come from. What happens when that forms? And the first thing that happens, you got this hot gas. It's kind of diffuse, right? It's not very high pressure, but you got a hot gas, and it goes through something called the condensation sequence. That's where all the chemical elements that we now recognize as having been produced in earlier suns and being blown out to interstellar space kind of gather together, condense on themselves, cool, and make particles. And then after that, we'll talk a little bit about planetesimal accretion. Those are like the protoplanet stuff and the early evolution of the solar system. This is going to include a bunch of isotope considerations. So the radioactivity I talked about last time will be important. This is not like dating with stuff that's been decaying all this time. Instead, this is looking at some of those not too short-lived R and S process nuclides, ones that were made, previous to our sun, that only lasted for some period of time. Some of them have really short half-lives. Some of them have, meaning on this perspective, tens of thousands of years. Some of them have kind of millions of years half-lives. So if we find that as we're cooling stuff out of a gas, and we get different amounts of these, then that means that they were still alive at that time, which means that we have to be in a short enough period since the last R process event to still have them, right? And we'll see there's some of these time scales between when we're just like a ball of gas that starts to cool and make particles, and then we've got little planetary bodies, can be measured in millions of years. It's pretty crazy, even to the point of making those little things come together, thermally reset, heat up, and start to differentiate into small bodies that have, a silicate mantle-like material and an iron-rich core. Again, can be measured in like tens of millions of years. So even though this happened a really long time ago, we think there was like a very compressed time scale over which we went from gas to small protoplanets. And then we go, from there into making the planets themselves. And we'll talk about that aspect next week. How do we know we got the Earth and we built it up? So we got to talk in between about, some of the building block materials for the solar system, which are recorded in meteorites. And there's a whole sort of variety of them. We're only going to kind of skim the surface of that as part of the discussion today, but you'll see that there are basically materials that are very primitive that represent this, and there are materials that represent various periods of this, meaning like kind of the very small coming together particles without much thermal reset, and then greater and greater thermal reset and metamorphism to the point where the collisions are causing things to melt, and then we're segregating iron and that kind of stuff. And all of that can be seen in meteorites, and that's where we get the measurement of these timescales that I mentioned here. It's by looking in those materials. All right, so last time we talked about the fact that our solar nebula, which is the name of the cloud of gas and dust that was circulating and eventually condensed to become our sun and our solar system, that the materials that are in it come from something before it formed, right? And we know that since that time, the only thing that's really changed in terms of the abundance of our sun is that it's fused some hydrogen to helium, but can't do anything else, can't do any of the rest of the nucleosynthesis we talked about. So all the other chemical elements we have are there because of other stars that lived and died and blew their stuff out. And so there was some kind of mixing process. People look around, just even within our galaxy, at different stars, and they can see that they're not all the same composition, right? There was some kind of basic heterogeneity that existed. We don't assume that all the kind of interstellar compositional particulates that come together to condense to make nebulae are the same. And if you think about it, stars that are older and condensed from nebulae earlier in the process are going to have a different composition than ones that have happened more recently, because we're continually making stuff. And stars are living, dying, blowing their stuff back into space. But the kind of two end members on this, and we talked about a little bit last time when we talked about the age of the universe relative to our solar system, is that there's some kind of statistical process that's kind of constantly happening, whether it's evenly spaced in time and whether the composition is exactly the same. We have to make some assumptions about that. It's kind of building up compositions in our neighborhood of the galaxy. And then there's also the fact that something happened right before our cloud of gas and dust condensed to give us some of these pretty short-lived isotopes. They're now gone, but the thing they decay into is something we can measure. And when we see the thing that they decay into, we can assume that when that material formed, that stuff was still alive. And so that constrains the last R process nucleosynthetic event before our cloud condensed. And as kind of a punchline to that, some people even argue that perhaps a supernova in our vicinity happened, sent a pressure wave that helped cause our cloud of gas and dust to coalesce and condense to the point that it could start to then gravitationally attract on itself. Because that's really what needs to happen. You got this material floating out there, and it needs to be able to condense on itself enough that it starts to get hot, and then, you know, gravitationally attract more and more material until you get to the point of having a star, which can then start to do the hydrogen burning. So I guess I have one little point here. I just took this image off of a news website from MIT, but one thing that people estimate is that perhaps the time scale to go from this, like a cloud of gas and dust, all the way to starting to have the gassy giants is just like 4 million years. And if you read this little news blurb at this thing, this argument's not made on radioactivity or you know, the level of our process things. It has to do with the conditions that must have existed to allow, you know, planets to grow to a certain point to then be able to pull gas to them, kind of more gas than we might have expected in their region from the sun. And we'll go through some of this detail in a few slides. But yeah, it's like a modeling exercise, but it's consistent, at least roughly, you know, in the sort of plus minus a factor of 2 with what we get from the radiation. So kind of the things you want to think about is you got this cloud of gas and dust. It's really diffused, and you know, it may have started out room temperature or something cold, maybe even less than room temperature because it's interstellar space. But at some point it starts to heat up, right? And so one of the assumptions that many people made for a long time is that our solar nebula was completely gas, and it starts to cool. And in that context, you can divide stuff up into kind of 3 types of materials. Stuff that's just never going to condense, right? It's always going to be a gas, no matter how cold you make it. Stuff that at high temperature will be a gas. You can see the elements of life here, the rare gases, halogens, that kind of stuff. But as it cools down, they condense, right? You can already sort of picture our solar system and kind of places where it's closer to the sun, it's warmer, and it gets cooler as you go out. So as you can imagine, you get more of this stuff condensing the farther out you get from the sun because it's cooler, and you can separate out between these different groups based on what their kind of Henry's law properties are for what temperature and what pressure they particularly come out. And then we've got this other group here, the oxides, the rocky materials, which form the rocky planets. And you can see here, even iron and nickel, which later become reduced and go into our core, they start out probably as oxides. And we're going to look at the thermodynamics of that next. And like I say, this is one way you can categorize stuff. You can use different names. People have toyed around with these kind of things, but the important thing to look at are the abundances for now. And we talked about the abundances last time, right? So most of the material in our solar system, in our sun, in most other solar systems like us, are some combination of hydrogen and helium, right? At 98% of the material. And if you look at the solar abundance material that we talked about last time, of this 98%, something like 94, 95% of it is hydrogen. And I think just for a second back to our low temperature geochemistry, when we talked about the EH-pH diagram, we looked at the stability field for hydrogen, water, and oxygen. When you got hydrogen, especially in this abundance, not only do you not have water, most of your other elements that can be reduced are reduced. So one of the things that happens is a solar system such as ours starts to cool and condense. This stuff starts to go away, right? We don't have this on Earth anymore. That's one of the sort of early oxidation events that allows the planet, this stuff blows away. Our planet isn't massive enough to hold these things. Something like Jupiter is massive enough to hold it, right? So that difference, that distinction, and how fast it happened and where it happened, and it happened as a gradient as we move out from the sun, or and in what conditions, affects not only how much of these things we have, but what oxidation state they're in. Okay, so that's kind of an important aspect of this whole discussion. So you can find these kind of graphics in Google Images. This is basically a really simplified version of a diagram that says that as a solar nebula is condensing, there's some distance from the sun. It's like a frost line, if you will, right? Meaning the place where these things will start to condense. It's cool enough for them to condense. And one of the big questions about this is not necessarily the temperature, but the pressure. Because if you think about it, right, the lower the pressure, total pressure, the harder it is to get gases to condense into either liquids or solids. And so making some estimates of, well, what was the temperature gradient and what was the pressure gradient is something that people do by making models and calculating what they expect, and then looking for materials in the solar system that might record that history. And so what we're trying to find are the materials that have experienced the least change since the early days of the solar system, the things that haven't come together. And so this is, for instance, interplanetary dust particles, some of the very small undifferentiated meteorites. I mean, we know the stuff falls to Earth, we know it's out there, even if we don't necessarily, say, oh, we're going to go to that object and collect stuff from it. For these earliest materials, because most of the objects out there have already been thermally metamorphosed, they've combined with each other, and all this kind of stuff. There's one other thing I want to point out, which is in both of these images, and the kind of idea that you start out with a pure gas and that you're condensing, no, excuse me, I skipped over this thing, condensing, some combination of these, something that we've learned in, I would say, the last decade or so, is that some of the most primitive meteorites, the C1 chondrites, have something called pre-solar grains in them. Little bits of solid, not much, but you can find it in the matrix, and some of them, little bits of solid that were never a gas, right? They were incorporated into our cloud. You could argue, well, where did that happen from? Was it somehow like above and below the plane of our orbiting nebular disk, or was it somehow on the outside? And again, people have theories about where this comes from. There isn't a lot of it. A lot of that stuff gets thermally reset as you start to build up particles and make planetesimals and so forth, but some of it doesn't. And so there are some phases in these interplanetary dust particles, such as diamond, very, very small microdiamonds, that record some of the conditions that were happening in our neighborhood of space before our nebula condensed. So there's basically, if you think about the whole sort of pantheon of processes. We say Earth formed at, whatever, 4.56 billion years ago, and we think that there was some number of things that were happening in the, 0.01 billion years before that, right? The gas condensing, doing all this stuff. But there are also some particles out there that are older than that, and that predate our solar nebula and manage to not be completely rehomogenized and processed and heated. And so that adds to the story. It tells a little bit more about what's happening in our neighborhood before our sun forms. So this is something called the condensation sequence. We're going to dissect it for the next few minutes or so. Temperature, right? And it's cooling, so it's high up here and low down here. And this is high temperature, right? These are in Kelvin, so 2000 down to 1100. And this is log of pressure, right? So in bar, right? And so a log of 0, right, would be 1, and that's, like atmospheric pressure like we have here on Earth. And that's like easy to do experiments in, but those conditions probably didn't exist in most places of our solar nebula disk, right? Pressures were a lot lower. People kind of argue about this, but probably somewhere in the 10 to the minus 3, 10 to the minus 4 range for a lot of it, except maybe, right where the sun was, where it's higher. But as you can imagine, because of the spinning cloud of gas and dust, as it starts to condense in on itself, it again gets more material near its center, gravitationally attracting to it. So the pressure will be higher near the center and lesser near the outsides. There's also some release of energy associated with that process, so it's also hotter at the center. So we're operating over a variety of places, and what people do is they make thermodynamic calculations we're going to walk you through in a second for, all right, let's say we start at this pressure and we come down. We start at this pressure and we come down. What does that end up meaning for us? I'm just going to check to make sure we're still on screen. Yeah. For the sequence of events and the sequence of, therefore, of solids we expect to find. And then we look for these materials, these so-called carbonaceous chondrites, C1, C2, C3, and we'll get into their nomenclature in a second. And we look, well, do we see these materials or not? Right? If you cool on a trajectory like this, the first thing that you would expect to come out of the vapor is corundum. Okay, and then some other mineral phases. Some of them are quite obscure and rare, ones that you wouldn't have experienced in igneous petrology. But for instance, you can start to see here. Here's the first place where metal shows up, right? So again, depending on the conditions, you might start to condense out some metal or not. There's also a lot of possibility for as a particulate is falling through this trajectory, cooling down at a given pressure. All those materials may not stay together, right? This may not be like a jawbreaker where you have some of this and you coat it with some of this and some of this. The particles can move and separate. They can also start to collide with each other. And then some of these minerals change into other things, right? If the conditions of temperature or pressure really change. So this is, again, one of the big questions we have about it. It's like, well, so did we cool all the way down to something really cold and make all these aggregate materials that are predicted by this sequence and then start to collide them together and heat back up? Or did we heat up along the way? And in what places did we do one thing or another? And the sort of short answer is that both of these things were happening. And at some point, like for instance, when you start to condense a metal phase, is much more dense, right? More like a factor of 3 more dense than a silicate phase, which makes it heavier if it's substantial in size and allows it to physically separate from the silicate phases. And so you might start to get distinction between the kind of metallic materials and the silicate materials as you're building up a planet. That's a process we'll talk about in coming weeks that people call heterogeneous accretion. Most people prefer for our planet something called homogeneous accretion, which means that you cool all the way down, not all the way, but most of the way down, make materials that then collide and heat up with each other. And as we'll get to later on in coming weeks, our homogeneous accretion is not purely homogeneous. Like we know stuff was added to, we know there was some subtraction. We had a proto-atmosphere that was blown away, for instance. And so there's something they call the late veneer, which is infalling material that comes in and adds composition to the Earth after it's mostly condensed. So this is a pretty complete diagram. It doesn't have the trace elements. There's actually some elements that are sort of less volatile at a given pressure than corundum. And I'll show you them on another slide. So osmium happens to be one of them. But this has a lot of minerals on it, and the main ones we would expect to see. I have a simplified version of it too. And these come from this kind of Planetary Society, website where they just describe this, if you want to go look and read at it a little bit more. But the key point is oxide phases that don't have silicon in them first, then various silicate phases that do have these elements in them, and some additional oxides, things like titanium oxide and so forth, but a mixture of kind of no silicate and then silicate plus non-silicate materials, and then no. That's kind of the sequence that I want you to kind of remember. And that sequence is true whether you start at a very low pressure or a very high pressure. And obviously, what's shown on here doesn't even get to the temperatures. Down here at 1100, is the ices won't condense yet. So if we go back to that table I showed you over here, that is just condensing this stuff. That's when people talk about the condensation sequence. They're mostly talking about this. There's a lot that starts to happen when you get cool enough to start to condense this that will disrupt. We can predict what all these things are, but it's harder to find these materials mixed with these materials in the proportion that would suggest that we cooled all the way down to something like 300 or 400 degrees. You'd have to continue these diagrams, way below the page to get down to the temperature where the ices start to come. Okay, so I just want to briefly talk about, well, how do you figure out that sequence, right? And it's a really simple set of equations and ideas. And, basically what we're doing is getting the abundance of every element, right? Considering its chemical form in the presence of hydrogen, that thing I just said about redox, and then calculating using the equilibrium constant of formation for a whole bunch of different materials, like corundum, the very top one on there, and I'm going to go through that example for you. Looking at its equilibrium constant between taking a gas of aluminum and a gas of oxygen and making it into solid corundum as a function of pressure and temperature, right, which are things that can be quantified in the laboratory, and comparing that as a function of, for instance, the equilibrium constant as a function of temperature, with what we calculate to be the abundance of the elements using a reaction coefficient. Remember, Q is written like an equilibrium constant, but it's the actual proportion of things that are present. We get that from those solar abundances, which we talked about last time. That tells us how much is actually there. So we take the ratio of how much is actually in the gas. We look at how this varies as a function of temperature. And then we calculate what's the temperature that stuff's going to come out. And we do that for a whole bunch of phases. And when people did these calculations, they included a bunch of other phases too, and then found out, well, that's not the top one, so it's not on the diagram, right? This is the one that as you're going down, each one of these colored bands represents the next thing to come out under those conditions. And so it's why it's kind of important to look across a range of pressures and temperatures. You will see that none of these things, they kind of overlap on each other and so forth. And like, you have to get to very high pressure to start, making this. I forgot what it is, but here, graphite. But other than that one, most of these things are subparallel, right? It's not like they're crisscrossing as a function of pressure and temperature. So really looking at the abundance of these things and what temperature they come out, you can kind of see the range here, like, as I say, this is kind of the range that we use for most of the solar system in here. We're looking at temperature like kind of 1800, 1700, maybe down to this. It's hot, hotter than magmatic processes on Earth today. We don't get magmas that hot. Okay, so this is, for instance, a phase diagram for silicon coming out, right? So this is temperature. You can see here it goes up to about 1600. Well, I've added in up to 1600. I went to 1550. And this is the percent of the total silicon. So imagine if you're on a cooling trajectory, you're coming this way, right? There's no pressure on this diagram. You could do a PT diagram, but instead this is what's looking at the cumulative fraction of silicon. So you can see here where silicon is as a vapor phase, right? And it can be as a vapor. It's not Si. It's either Si with sulfur or Si with oxygen. Again, the proportion of these two things is based on someone looking at the abundance of the elements, looking at the relative amount of sulfur that's present, the relative amount of oxygen that's present in our sun, using the equilibrium constant of formation, and that's how this proportion is calculated, right? So you start to cool down, and as you cool down, you add more and more stuff into the solid phase, right? So you're cooling, you hit this trajectory. I've extended this up because I think people believe mellow light forms at higher temperature than this. But then, you follow this trajectory and you start to get different minerals, right? Pyroxene minerals, olivine minerals, more pyroxene minerals, et cetera, et cetera. And so again, that tells us that for the silicon, these are the phases we expect to see it in, right? And if we find this stuff, then that might say, oh, okay, that's a really high temperature material. Sometimes this stuff, later with the thermal reset that we talked about, the metamorphism goes away. Here's another example. This is calcium coming out, right? So calcium, unlike silicon, which combined with either sulfur oxygen, it is just as pure calcium in a gas, and it starts to cool. And the first thing it goes into is that same phase called melolite, right? There's a small amount of perovskite that's also formed, but then as things start to cool, then dioxide becomes stable instead, right? So then you start to put, but you've already condensed. This is the curve that goes from gas to solid, right? But then if you keep cooling, right, then the conditions of formation would favor dioxide. But in this case, we only expect our calcium in the oldest materials that have been reset to be in one of these two phases, because they're the only ones that touch the gas. This is aluminum, a little bit more complicated. You can see here in the gas phase, some of it is metallic aluminum, some is a hydroxide, very small amounts is either a hydride or a fluoride, and it comes out in all those cases to make corundum, okay? And then as we continue to cool down, aluminum can go into melolite. But again, if we find corundum, that means we were at temperature conditions that were hot enough to allow this stuff to form before this stuff forms, right? And so at the time that this is happening, we're not even making this stuff. This is why, if you go back to the condensation sequence, you see corundum here, right? Melolite is below it. Does this all make sense? Okay, so this is a very simplified version of a cooling trajectory as a function of different partial pressures. Remember, we said as we're going out along our nebular disk, pressure is getting lower and lower. We don't know exactly what it was. I said before that many people use a value of 10 to the minus 3 to 10 to the minus 4 for most of our disks, especially in the vicinity of our sun, of Earth. Probably gets higher as we get closer to the sun, it gets lower as you get further out. But so at a given pressure, and these are again based on laboratory experiments, you can look at, well, what would cooling look like, right? So cooling comes down, right? And it's not exactly flat. The pressure does start to change a little bit as you cool. But you can see here that again, for the most part, except for the metallic iron, these lines don't crisscross each other, right? The sequence is the same. The exact value of the temperature and the pressure are codependent and vary, but it's only when we start to get down to the condition of making metallic iron that, depending on the pressure, high pressure versus low pressure, is either going to come out before the olivine or after. That's what this is. Okay, so again, when we start to look in the building blocks of materials that make up the planets, one question we might ask is, well, under conditions where it happens at very high pressure, do we start to segregate a metallic phase out early? And does that help us explain, for instance, why some of the planets that are very close to the sun, such as Mercury, have a different density? Because maybe iron started to come out of the gas phase before a lot of the bulk silicate, and because of that, it may have accumulated gravitationally, so that the planets in these conditions may have gotten extra iron, maybe more than once at a lower pressure. So this is basically just a calculation where we look at the chemical reaction. This is the one for corundum, solid, gases, right? And these are the atoms, and calculate an equilibrium constant. We don't put in the solid, so it's just a partial pressure of aluminum squared and a partial pressure of oxygen to the third, what we get from it. So you can write this out using our favorite format of taking the log of both sides. This is log K equals this, right? And so we can then figure out, I guess let me just go back for a second. We can figure out what we're going to plug in here for the partial pressure of aluminum and the partial pressure of oxygen, making a few assumptions. We're going to take the abundance in our sun of the relative amount of these things. We're going to compare them, because they're partial pressures, to the amount of hydrogen, because that's the thing that sets the total pressure. So we're going to look at the ratios of elements to hydrogens, and if you saw, that was one of the things we talked about last time, right? And so to make that assumption, there's two other things we have to do. We're going to assume the nebula is an ideal gas, where PV equals nRT holds, right? And it's pretty low pressure, so it's probably okay. It's not exactly, there's probably some activity coefficient action going on there, but for the purposes of these calculations, they're not that important. So the total pressure times the volume, and we're going to just use unit volume, equals the number of moles in that unit volume, the gas constant times the temperature. So that's where the temperature comes from, right? So we've already seen, we've got a P and a T. We've already calculated those things. That's what comes out of these phase diagrams, right? And now we're going to say, well, what is this P made up of? And we're going to make the assumption it's pretty much all hydrogen. Not hydrogen is H, hydrogen is H2, which is what it is when it starts to cool, right? And here's some of the rationale for this, right? But when we look at the abundance ratio, for instance, helium, the next most abundant thing in our solar system and in our sun, to hydrogen, it's about 6% of the total, right? The hydrogen really makes up the most, and all the other elements are like 0.1%. Okay, so using hydrogen in this form, H2, as P total, it's an approximation, but it's a pretty good one because, like I say, 94% of the material in our solar system is there. Okay, and so there's a couple of other little tricks in here that you go into. If we look at the abundances of the elements, those are given as per element, whereas H2 is got two hydrogens together, so we have to divide by 2, right, to get so that the partial pressure of hydrogen is half the number of atoms of hydrogen that are present because it's hydrogen as a gas, okay? And then we start with a pressure total, again, 10 to the minus 4, 10 to the minus 3, as I mentioned before. So this is the value that goes in here. But then we're going to look at ratios of other elements to the hydrogen, right, that we get from the abundance of the elements. But we're going to divide the hydrogen by 2, right, cut it in half because it says H2. And then those are going to give us the partial pressures of our other gases that we can stick into these equilibrium constant equations. Okay, so we derive an expression which says that the number for any given chemical in this solar nebular gas is its mole fraction, which is what we calculate from the abundances, 2 times the pressure of hydrogen times or divided by RT. Okay, and this is just something that we can plot, and we're going to calculate this per unit volume, as I say. So, like, 1 liter of gas. Okay, and then we put this up on a diagram. So this is the equilibrium constant, okay, as it varies with temperature, right? And it's written out this way in these units, the log K units that I talked about. So this is actually log K units, and this is the reaction coefficient, the actual proportion of stuff that is present. Okay, and so how you calculate the condensation conditions is you basically look at the intersection of these two lines, and that tells us the temperature where this stuff's going to come out at a given pressure. So you can do this at 10 to the minus 3, 10 to the minus 4, or 5 times 10 to the minus 3, whatever you want to do. And you calculate a bunch of different values. And so this point, which is this happens to be the one for corundum, calculated at a bunch of different pressures, is what makes up a diagram like this. Right? This is how we get this line for corundum in pressure temperature space. Okay, so this is a slightly fuller version of the condensation sequence from one of the very earliest papers in 1974 when it was first kind of worked out and calculated. And so you've got a gas phase over here. You can see how high the temperature is, and you start to bring stuff out. And so you can see here that there's some stuff that starts to come out of the gas phase way before we start to make corundum. So here's corundum here. So some osmium, really high temperature element, zirconium as a metal, and then zirconium and zirconium oxide, rhenium. So rhenium osmium is a radiometric dating system. Those guys sit, here's rhenium and here's osmium, okay? That because they both condense really high temperature, they tell us if we can use the radioactivity in this system where isotope rhenium decays isotope osmium tells us about very, very early evolutionary timescales in this system in conditions. Another thing that's up here at very high temperatures are the rare earth elements, tantalum, niobium, uranium, plutonium, and thorium. Okay, so rare earths, these dudes down here, right? The thorium and the uranium are just below them. And remember, you've probably heard thorium uranium dating is one of the ways that we know the age of the Earth and stuff. And this is part of the reason that they work so well is that they're what we call refractory. They are so high temperature in the gas phase that very little, anything that happens after the fact, kind of thermal resetting and metamorphism tends not to perturb these things. When we look at materials collected from around the solar system, we see more commonly, not in every material, but more commonly the same proportions of all these refractory elements in the osmium and the rhenium and the zirconium in each different thing. Like we look at the moon, we can look at the sun, we can look at Earth, we can look at meteorites. We always see roughly the same proportion of those things, which tells us that these very high temperature refractory materials were somehow, for the most part, preserved in the same proportion. And all the other chemical elements that are much more sensitive to perturbations in temperature and conditions in pressure, they have more variations. And so what we oftentimes do is look at the ratios, and we'll see this later when we start to talk about the mantle and the composition that we find in rocks, like in Hawaii and other places. There's some elements that are in a special category, in part because we can make predictions about what the very early Earth had in them based on looking on these other materials and the constancy of those elements. But then, you keep coming down, and here you start to get the corundum, and then here you get the melolite. And as you can see down again, there's a bunch of different phases that are present. But for instance, you don't even find the feldspars until really low temperature. And this is when you really start to pull out the alkali metals, you guys over here. Okay, and so you can imagine if there's something that's going on as we're cooling that causes materials to separate from each other, it might cause the Earth to build up with kind of more or less of this than some of these other elements because they got separated. We'll also find that late in the planetary accretion sequence, when we start to have large-scale impactors hitting other planetary bodies, conditions can get hot enough that some of this stuff evaporates again. We'll see that near the end of the day when we look at the potassium-uranium ratio for Earth and the Moon. I'm just looking at the time. Okay, so another kind of key thing I want to point out to you is down here. So here's we've got the sulfur. This is a mineral called troilite, iron sulfide, and then lead and bismuth, thallium, indium. These are elements that are sitting over here, right? The metalloids, they're volatile. We actually see them coming back out at volcanoes such as Kilauea. Not all of it, but little bits of it you can see in the vapors. About 1% or so of the lead comes out. And then all the way down here, you get hydrated silicates, clay minerals, for instance, right? So when we look at meteorites, and if we find this stuff and we think it's in the proportion that we expect from having gone through this sequence, then it tells us, well, there's a material that managed to go all the way through, right? We can also make hydrated silicates in secondary processes and other things, so we need to be able to distinguish them. But there are a class of meteorites called C1 chondrites that we're going to talk about in a moment that record this whole sequence, right? Plus minus, nothing's perfect, but they're pretty darn close. So this is just a table showing you some of the condensation temperatures and giving you some names and some, whatever mineral formulas in case you want to look them up. This is a periodic chart of the planet that has been color coded to put things into 5 categories. Early condensate, those are the refractory elements, right? And you can see which ones they are. They're all these kind of beigey colored ones. The only major element in this category is aluminum, okay? Corundum. And then we get down to the next, well, actually calcium is pretty major too, but in terms of the main building blocks of the planet, we don't have the silicon, we don't have the iron in there yet. Then things cool down a little bit more based on the condensation sequence, and then we start to bring out silicate phases and metallic phases, and so we can see which elements are associated with them. The metallic phases, as they condense, not only is there iron, but the chromium, the cobalt, the nickel, the palladium, the gold, phosphorus, and arsenic start to condense into those materials. And at the same time, the silicate phases start to form, and we start to pull in the lithium, the magnesium, and obviously some oxygen. Then we cool more, and what are called volatiles in this context start coming out at 1300 degrees, right? That is pretty hot, right? But from 1300 down to 600, we have what we call the high temperature volatiles, and those are, the alkali metals, as we talked about, plus some of these transition metals and some of these metalloids, okay, including the sulfur, which is kind of important, because one of the questions we have is, well, how much sulfur might combine with how much iron to go into a protoplanetary core? And it kind of depends on what the cooling trajectory was. Do we have iron metal present or not as we start to get down to the temperature where this stuff starts to condense, which, if you recall, is a function of pressure. And then we get the elements that only condense below 600 degrees. You know, things that are highly volatile. Obviously, the noble gases, the halogens, bromine, carbon, nitrogen, boron, carbon, nitrogen, oxygen, elements of life. Things like mercury. And so the amount of these things that we can find in some of these early planetary materials or protoplanetary materials also tells us something about, well, how cold did it get before stuff starts heating up again when things are coming together and melting and colliding, etc. So this is White's idea of the condensation sequence. It's similar to what you saw before, but, and I'm not going to kind of walk through it. I've given you some of the key features of it. You know, the very refractory elements, which he doesn't even list, just like that condensation sequence. He starts with corundum. These other things that volumetrically they're a very small component, but chemically they're super important. So I'm kind of surprised that Bill didn't include that. But in any event, we make the corundum. At the same time, we're pulling out some of these refractory elements. Things cool a little bit more, and then we start to pull out the perovskite. That was in the first diagram I showed you. And then you start to get to silicate materials and the iron nickel alloys, and then you get to the feldspars, and then sulfides, and then hydrate created phases. And those are kind of shown here, sort of following through some of the elements in this process. Like all the ones, you know, here are sort of the phase that has iron. Okay, so we see remnants of this sequence in something called chondrites. Chondrites have a whole bunch of different categories. The kinds of chondrites that have carbon in them are called carbonaceous chondrites. And they are further categorized as C1 to C5 based on how much thermal metamorphism they've experienced, right? So C1 is the less metamorphosed, C5 is the most metamorphosed. All of them are very unmetamorphosed compared to other materials in the solar system, and in part because they contain a lot of carbonaceous material. But in any event, these materials are basically sedimentary rocks, plus minus a little bit of metamorphism of the condensation sequence. And so we look at them and we want to talk about them in a little bit. But some of the stuff that we've learned over the last several decades is that, you know, there are different carbonaceous chondrites that fall to Earth. Each one tells a slightly different story. And they give us the idea that it wasn't a single cooling from hot to cold making these meteorites. There were pulses of heating during the cooling. And the pulses of heating make something called chondrules, which is where the name chondrite comes from. Chondrules are little balls of silicate glass that are little droplets. We'll see some pictures of them in a second. But the fact that they're present probably implies some amount of thermal reset and heating. And they're what distinguish the chondrites from every other kind of meteorite. Most of the meteorites don't have any chondrules in them because of continual thermal resetting, which causes those things to melt and rehomogenize back into the material. And also, as I mentioned previously, there's some of these pre-solar grains in there. Okay, so there's a sequence that says, yeah, what we predict from the pure equilibrium condensation sequence is close to what we see in carbonaceous chondrites if we kind of, you know, ignore the pre-solar grains, which are small and important, but they're there. So not everything was a gas ever. And there are some chemical reactions that can happen as things are cooling, that as predicted by the condensation sequence, but we see them, and they play a role in some of the details, and this idea of kind of multiple periods of heating and cooling as things condense. But so think about the gradient from the sun to the edge of the solar system. We're in a nebula. It's a disk. It's not like a record album, but it's a pretty flat disk. And so material that starts to gravitationally attract and condense and collide and make smaller particles grow into bigger particles that become planetesimals and start to accumulate along the disk itself. They're going through different temperature trajectories. right? Temperature and pressure reactors. And so particles that condense out by, where Neptune is or out where Pluto are, they're going to go through a different cooling trajectory than ones that, fall in right near the sun, such as in the vicinity of Mercury or in the vicinity of Earth and Venus. We have to account for that in the idea when we look at the distribution of chemicals that we now find in the planets. We have to ask ourselves how much of it was differences that were happening in the gas as the condensation sequence was happening as a function of pressure and temperature, and or other physical processes that could happen that could cause the aggregation of some material. If it happens while we're still cooling, for instance, and that will just determine how much of the gas phase gets held onto any individual planetary body. Okay, so this is another way of looking at the evolution of planetary material by dividing them up into sort of three categories: an early condensate, metal, and silicate, right? And cooling down, right? And then, as I've added in the same color scheme as that other diagram with the periodic chart, we start to then incorporate the high temperature volatiles and the low temperature volatiles. And we can track each of these materials together. This one doesn't really change the whole way down. That's why the refractories are so useful for us in studying early solar system processes. The metallic phase will change. It'll change what it has in it. It'll start to incorporate some of the volatile elements. You can see here copper and gallium and germanium and tin, for instance. Maybe start to get some thallium or some lead in there, incorporate some sulfide, et cetera, The silicates will also transition as we go down. And the two things that are kind of important in this diagram is here, once we get down below 700 degrees or so, we start to have chemical reactions, right? With either H2S or H2O, and that's going to change what these phases are, right? And then here, we get to this point of perhaps remelting and accretion. And this is just one person's model of saying, yeah, we cooled all the way down to 500 degrees before we started colliding stuff back together and heating things up. And, some meteorites give you this value as, yeah, that's probably right. Some of them it's higher temperature, some of them is lower temperature. So I just want you to get the idea of the concept, right? We build these materials together, and it would be great if everything cooled down completely to a solid and then started colliding and building things up. But that isn't exactly what we see. There's some complications, chemical reactions that happen. Okay. So now the next topic to talk about, and I'm going to do these two things together, is the accretion of planetesimals and what the early evolution of our solar system looked like. Okay. So this is a picture of one of the very first ever collected, so it's in 1995, of protoplanetary disk, right? It's kind of fuzzy, doesn't look so great. That's how things were back in the 90s. This is a Hubble telescope image, but not as computer processed as we have today. But even being able to identify a disk, and this is in the Orion Nebula with kind of a glowing hot center, and seeing this happen, it gave a lot of credence to the idea that, hey man, these things actually happen. Now you can go on Google Images and see protoplanetary disks, which is another term for solar nebula, up the wazoo. They're all over the place. I think the question that cosmochemists ask and astronomers is, how do you go from one of these things, right? These disks, and they don't all have the same shape. Some of them are very irregular. Some of them, are bigger, and some of them are smaller. And but you end up at the end with a star, right? You got some planets. You got some satellites like our moon. You got some really fine particles, and you got some gas, right? And so we know what the beginning sequence was, plus minus, it was this condensation sequence. And at the end, we know what it is here, and now we've got some other solar systems we can look at. We know what it is in those things too. And they're not all the same, but there are some similarities that we always find, such as, it's hotter near the sun than the star than it is going out from it. We find different proportions of some of the chemical elements in some of the stars, right? Based on the nucleosynthetic processes that cumulatively happened before that protoplanetary disk condensed. But beyond that, there's a lot of similarity between these various systems from place to place. These are just some other pictures of some protoplanetary disks, again, in the Orion Nebula. This is about a decade later, showing you some of the variety. And one of the interesting things that you can see in some of these cases is these sort of extended plumes of gas coming out, which are thought to reflect sort of being blown away by ultraviolet radiation from, another star in the region, having an impact on it as it's being formed. So I'm not an astronomer, I don't know this stuff in detail, but there's a lot that you can see when you look out there with these telescopes. So this is basically what we have today, right? We've got, when we look at distance from the sun going out, and we look at the density of the planetary bodies, okay? We have, obviously, Mercury and Venus and Earth, and then we go to, we continue along, and there's a big change in density when we get, so the gas giant planets that, Jupiter, Saturn, they're really low in density. It kicks back up a little bit again. And in fact, people have argued that there were processes that probably went on that caused these guys to accumulate a little bit more gas than we would have predicted early on, maybe because they grew massive more quickly, and that gives them the gravitational attraction to pull stuff in. Other people have argued that, well, maybe Saturn, for instance, actually formed further out and then migrated its orbit in. That's not as popular of a theory. But the key thing is that the stony planets are up here. Then there's this transition zone, which includes the asteroid belt. And look how small they are. I mean, these are depictions, is a graphical representation, but of their size and their density. There's something key difference. And so we distinguish what we call the stony planets and the gassy planets, right? And there's variations within them. But it's like, for instance, we want to understand the variations in density between these planets here and the ones that are further out. We want to understand the density differences between these and so forth. Remember back when we talked about the frost line at the very beginning stage, the frost line is playing some of the role between stony and gassy, right? The ability to condense a lot of those low pressure phases and hold them to the planet. The planet has to gain a certain amount of mass to be big enough to be able to hold elements to it that would otherwise, some fraction of them have an escape velocity to leave the atmosphere. Like for us, some fraction of our hydrogen that we formed with is still leaving the atmosphere every year. Our planet's only massive enough, massive enough to hold everything except hydrogen and helium. So some of that stuff's leaking out the top, but pretty much everything else stays. But something that's even smaller, right, like the moon, it can't really hold very much. So you've got a spinning protoplanetary disk, right, with dust-sized particles that primarily came from the condensation sequence, right? And these things start to collide with each other. There's some probably number density variations that go out along the disk, more in the center, less around the outside, because the disk itself, while it was still hot and was spinning, was gravitationally attracting in on itself and accumulating more material near the center, right? Even to the extent that it's allowing the proto-sun to start doing its nuclear fusion, right? Get pressure high enough that you can start to have a glowing object, right? And so there's variations in that. And people do these calculations, they're primarily statistical, where they look at, okay, you've got some particles and every once in a while they're going to hit each other, right? And then under what conditions do they hit, and do they stick together and build up aggregate particles that are bigger and bigger? And when they get to a certain mass, they start to release more energy as they impact on each other. Is that enough energy to sort of thermally reset things? And the answer is yes. And so you make up small little materials that we call planetesimals, which continue to get bigger and bigger by kind of sweeping, they're spinning around in this disk and they're sweeping out all the material around them, right? And this is in essence how we get planets, okay? It's a dirty process, it's a little bit more complicated than that, but materials are colliding, collecting, getting bigger. This is a very common early graphic from this Australian guy, Ringwood, wrote this book, Origin of the Earth and the Moon. It was big in the 60s and 70s. You can find newer versions of this diagram, but I always like to go back to the very earliest ones, right? And so this is the Schmidt and Safronov model, right? You've got a protoplanetary disk with a sun and basically a cloud of gas. One AU is the distance from Earth to the sun, right? So this is at 10 atomic units wide. It's spinning, things are colliding with each other and building up in size. You start to make, these particles are sort of sweeping through their angular area, right? Because there's collisions, some of these collisions cause the angular momentum of the growing particles to start to deviate from this disk. And so we start to get some stuff that's kind of on weird trajectories relative to the plane. That continues. At some point, things settle back down where now all of a sudden we've got planets, right? We've swept up most of this material, not all of it. We can still find remnants of this stuff, in the interplanetary dust particles. But, the question of how long did this take? What were the conditions, thermally, pressure, time? Those three things are really important. Are things that they're still very active areas of research. We kind of have an idea of what the boundary conditions are for the pressure, temperature, and timing, and it's remarkably fast. As I mentioned at the beginning, on one of the very first slides, people feel like it's possible that we went all the way from this to all the way to this in something less than 10 million years. Right? Which, I know it sounds long, but on the time scale of how much other stuff we've been talking about is short. It's just another kind of simplified version of that graph. Okay, so you can think about what were the conditions like in this protoplanetary disk. And one thing we know, because of the temperature gradient, right, that when we're near the center of that disk, the only thing that can condense are the high temperature oxides, the refractories, the melolite, the osmium, the rhenium, the corundum, that kind of stuff. And as we go further out, where it will ultimately get cooler, right? Because right at the proto-sun, it's hot. It's too hot for that stuff to ever condense. We don't go through the whole condensation sequence. Then we start to get to the point where we can condense this stuff. But it's too hot for us to ever condense a significant fraction of the volatile elements, right? And so even though we have, thank goodness, we've got carbon, we got oxygen, we got nitrogen on the planet, we got a lot less than the solar abundance would tell us we should have. Most of it is gone, got blown away. And some of it accumulates out here in this part of the solar system. So part of the reason that we've got, this distribution pattern of densities is that some of these grew bigger at the expense of some of the lower temperature part of the condensation sequence, that because conditions were too hot when these bodies were forming, it didn't condense, and they were sort of blown out, further out along the plane of our nebular disk, and then condensed onto other planets. Okay, so this is sort of just a slide that summarizes it. The condensation sequence works pretty well. We can find materials that look kind of like it. And they suggest that our cloud of gas and dust was rather uniform. Right? I emphasize the word rather. Right? We know it wasn't 100% uniform. We'll talk about some of that evidence in a second. But plus minus pretty good. And then the composition and density of the particles as they're building up into planetesimals reflect some kind of pressure temperature path that's a gradient as we move out along our disk, as well as the energy of the collisions that go on that build things up later in this process. And we're going to talk about this side next week and the week after when we talk about the accretion of the planets, because here we're thinking about one set of conditions, and here we're talking about, well, how big did things get, how fast, and how much energy was released when they collided, and what does that do to end up giving us planets that look like what we have, which are different in materials than this stuff that they originally formed. Okay, so the other things that people look at are variations in density, variations in surface composition, and these are just a couple of the things that there's a regular variation in density. You saw that as you move out, but there's some things that are a little bit hard to explain with a simple model of cooling and condensing in a spinning disk, such as Saturn and Jupiter have too much hydrogen and helium for what we would have thought compared to the ones further out. And there are some observed variations, some of the stony planets, which are also a little bit like, why is Earth more dense than Mercury and Venus? We'll get to some of these things later, but in coming weeks. But one of the things that people talk about is because the metallic phases are so much more dense than the silicate phases, that as you're cooling that stuff down, if you have the ability to separate those phases and get a little bit more metal in this planetary body, then it's going to be a little bit more dense. And that's this idea of heterogeneous accretion, which most of us, including myself, don't really believe happens to any appreciable extent. But anyway, it's one of the ways to make density variations. Another way to make density variations is to just tune the dial of how much oxygen do I have present when my iron phase is forming. Because iron oxide is going to be of a different density than iron, pure iron. There's also how much hydrogen happen to be around. Because if you stick hydrogen into your metallic body, you can also make it less dense. So there's other chemical knobs we can pull that can start to play some variation in the densities, especially on the iron-rich component that goes into making the planets. All right, so this is just a diagram showing you sort of surface density. So now we're not talking about the whole planet, but we're talking about the compositional density associated with the crust of each planetary body and distance from the sun again. And you can see there's kind of a main band, right? With Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. And then you can see Mercury, Mars, and the asteroids sitting a little bit lower. And people, there's various things that people have come up with to try and explain those things, which are kind of summarized here, but they're physical processes. So there's one other thing that I want to mention, which has been observed in other stars, right? Which is as a protoplanetary disk forms and gets to a very early young star, oftentimes they'll go through something called the T-Tauri phase, where it's super luminous, meaning it's burning hotter and doing more stuff, and then it chills out and settles down a little bit. And during that period of time, the solar wind can help to, not necessarily, we don't know that this happened in our sun, but we've seen it in other suns, can help to expel some of the original mass that's in close to the star, maybe as much as a quarter of it, and help push it out to the outer part of that solar system. And so this is another aspect that has thought to have played a role. People invoke this to look at the evolution of atmospheres. Like we know, and we'll talk about this in coming weeks, that the atmosphere we have on our planets was called a secondary atmosphere. This is not the atmosphere we condensed with. We lost a bunch of stuff early on. And then what made our atmosphere came out of our mantle. Right? It degassed and formed. And we have what we have, because the conditions that started to make the secondary atmosphere were arrived at after the phase where the blow-off happened. If it happened early, then we would have blown off all our atmosphere and we would have been out of luck because there wouldn't have been anything left. So there's some stuff that is good that it happened the way it did. All right, so here are 7 important things that tell us about planetary compositions, right? Questions that we have. Was a solar nebula homogeneous? Do the metals and silicates accrete together or separately? Do planetesimals accrete homogeneously or in stages? How long did it take? And when it was taking place, how much hydrogen was present or not, and at what temperature conditions? And this is going to set our redox. How do the moons form, right? And they don't all have to form in the same process. We think our moon formed from a collision, a big collision. We think some of the other moons didn't form that way. They were just incompletely accreted onto their planetary bodies. What causes the differences between the inner rocky planets and outer gassy planets? We've already kind of talked about. Why are Earth's 2 closest neighbors so different in surface temperature, atmospheric conditions, etc. And so we get some of these answers by looking at the starting materials, which are meteorites, which we're going to talk about next. And then some of these questions we'll start to answer as we build up over the coming weeks with other aspects. So now I just want to give you a primer on meteorites. This is a meteorite. You'll recognize some of these minerals. There's olivine and there's pyroxene in there, and there's a matrix. This is what's called a differentiated meteorite. It's not a chondrite. It's like a basalt, basically. It is from a planetary body that built up to the point that it heated up and it segregated out its metal. So it had a silicate phase and a metal phase, and we're looking at the silicate. Okay, so this is what's called a stony meteorite. We'll talk about this in more detail. This is kind of like the end of the process of making of planetary bodies, proto-planets, planetesimals. Okay, so when we talk about meteorites, we have sort of 3 categories, what we call stony, ones that we call metallic, and then we have mixed, stony ions. And they're really cool, right? They've got blobs of metal and blobs of silicate, and they tell us a lot, again, about the coexistence or the potential for coexistence of those condensation sequence parallel lineages in early planetary materials. Now, stony meteorites come in a couple categories. There's chondrites and achondrites. We've already talked about chondrites. They're these clastic sediments that they're more or less metamorphosed. They include the carbonaceous chondrites, which is just one category. Chondrites have to have the chondrules. The chondrules are little balls of glass that condense from a gas phase. And to have a chondrule means that you're probably from an undifferentiated, never heated up enough to rehomogenize that stuff. Then we have the achondrite. So that one I just showed you, that's an achondrite, okay? Because it's gotten to the point where whether there were chondrites in the original material that it was formed from or not, they collided together, and the planetary or protoplanetary body that it was sitting on before it got dislodged and fell to Earth was hot enough that the chondrules were gone. So we consider the chondrites to be the most primitive. We consider the carbonaceous chondrites to be the most primitive of them because they still hold their carbonaceous material. And there's all sorts of subclasses. This is like a really complicated thing where people look at the differences in the mineralogy and the composition and the textures, and then they, almost every meteorite can have its own category at some level if you get down detailed. So this is a picture of a carbonaceous chondrite. It happens to be called Allende. It fell and it was in Mexico. I can't remember if it was Mexico City or somewhere else, but and I think it fell in the 60s, but we could look this up. I'm not exactly sure, but you can see it's, like I say, it's a sedimentary rock. It's got a bunch of materials in it, which I'll show you on the next slide, that look as close to the condensation sequence as anything we can find in our solar system. They're not exact, but they're pretty darn close. So the things that are in there are the chondrules. These are the quenched glasses, what we call refractory inclusions, sometimes called CAIs, because they got a lot of calcium and aluminum as per the perovskite and corundum. And then we've got a matrix, right? And the matrix has a whole bunch of different stuff in it. It can be it is fine grained, but it's got some iron oxide, it's got some olivine, it's got some pyroxene, it's got carbonaceous materials, it's got low temperature phases like clays, right? And so this is reflecting that whole temperature sequence, the condensation sequence, and kind of putting it together in a way that makes it stick together as a rock, but doesn't make it hot enough to kind of lose the original proportions of stuff, plus, minus. Okay. So, and as I say, the carbonaceous chondrites are a category of them, and they're subclass with sort of least most metamorphosed. People talk about C1. You'll see C1 chondrite as being, a common thing that's used in geochemistry to talk about compositions that we think that was the Earth's starting material. Although most people now feel that C1 may have accumulated more of some of these icy components than Earth itself, that maybe Earth is more like a C3 chondrite, but this is a level of detail we don't have to worry about, I don't think.
So are all chondrites sedimentary rocks?
Yeah, I mean, and this is but sediments that form in a really different environment than sediments on Earth, right? So they're sediments in the sense that they've an aggregate of clastic particles that stick together, but at very low temperature without any kind of water involved. And so yeah, and most people would think of them as sediments. So this is just a picture of a slice through a carbonaceous chondrite. And so you can see here, these are what the chondrules are. There's very characteristic ball-shaped things. In this case, they're a little bit oxidized. That's why they're a little bit orange, but they're silicate glass, okay? This is what a CAI, one of these refractory inclusions look like. See how it's like very irregularly shaped. And you can have big ones, you can have small ones. There's heterogeneities in them and stuff. And then you have the matrix, right? And so this is a different meteorite. I forgot which I took a picture of it. This is in our collection. But carbonaceous, this one here has a different look than this one, right? And it could be just something to do with the conditions that it experienced on Earth once it fell and was sitting out there for a long time, and someone picks it up and slices it open, or it could be the conditions it formed with. And so, people analyze every aspect of these things to try and disentangle that history, that complicated history. So here's one of the cool things about carbonaceous chondrites. So these are C3 chondrites, right? Actually, that's a mistake. This plot is of C3, but this should say C1 up here. Sorry. And this is the composition in carbonaceous chondrites, and this is the composition of our sun, measured spectrally. And look at how close they line up with each other for most of the chemical elements. Yeah, I mean, some like little details here and here, like some stuff that's a little bit off, especially like these things. These are lower in chondrites than they are in the sun, and maybe that's because the conditions of condensation or whatever. But to a first order, these are the materials, the solids that we find in the solar system that look the most like our sun. Okay, and ordinary meteorites don't follow the same pattern. We can look at deviations that they have relative to that, and then start to say something like, oh, well, what were the conditions like when that one formed? Based on, for instance, the relative proportions of the elements that like to go with the metals, or the ones that are kind of a little bit volatile, or the ones that vary their composition as a function of oxygen fugacity or hydrogen. And so that's how we ultimately we're going to look at Earth compared to these chondrites. And what we will find is that some of the refractory elements, the dudes down over here, mostly they're very small, like here's the thorium, here's a rare earth, cerium, here's lanthanum. They also, Earth looks like this, right? So that the temperature, all the processes that go on to build up Earth, which tweak most of these other elements, they look a lot different than chondrites today than they used to. Some elements see through that whole process. And so we kind of use them and ratios of other things to them to understand the evolution of Earth. So this is another diagram from White, kind of showing you how might chondrites have formed, right? So you start out with a cloud of gas and dust, things start to cool down a little bit, and you start to separate out the CAIs, the refractory inclusions. Things continue to cool down, and there's perhaps processes of transient, so-called flash heating, like events that are causing heating and cooling as we're building stuff up. We're still talking about very small particles here, but those are the things that probably produce the first conflict, right? Chondrules are like droplets of silicate gas. And then they continue to cool, and we start to incorporate some of the other materials, the lower temperature parts of the condensation sequence. And then these little small rock-sized things need to build up into what we call a parent body. So every meteorite that falls to Earth, we assume, came from something bigger. It wasn't just a rock floating out there. It was something that, a collision happened on a planetary body, which people usually call parent bodies, meaning it was the thing from which that meteorite came from. So for instance, we have meteorites that we know came from a parent body of Mars. We have meteorites on Earth that we know came from the moon. We have ones that we know came from various asteroids. So that's what we're talking about, their parent body. So there was a general cooling. It was probably not a single one-way trip. There was, like I say, there was some of this flash heating, and some of the stuff can be told by looking at different populations of chondrites within an individual meteorite. But in the cases where they cool all the way down, we end up with chondritic meteorites with those proportions I showed you on the last slide. And during that process, there can be more or less amount of metamorphism, especially with the water that comes and elevated temperature. It can change some of the phases in the matrix and cause them to compositionally shift from, for instance, dry silicate to wet silicate in the process. Okay, so this is a plot now showing you that this is just like atomic number across the bottom, or element. They're not in any particular order. They're basically done in descending order of concentration as a ratio of what we think was in Earth's mantle relative to C1 chondrites. Okay? And we'll talk about how we get this. We can get this from various things, but we look at the very earliest silicate rocks that were formed on Earth. We look at xenoliths, the early mantle, and so forth. There's a whole bunch of elements that sit up here at 1. Our refractory elements, uranium's in there, thorium, it's not labeled, but it's up here, the rare earth elements. And then the magnesium, the aluminum, and the calcium, they're pretty close to a ratio of 1 to C1 chondrites. So if we assume that the planet built up from chondritic material, which is the basic assumption, there's a group of elements that are basically in the same proportion as in chondrites, which are in the same proportion as the sun. Then we go down to greater and greater degrees of depletion. Like our silicon's a little bit lower. It tells us that the pressure and temperature were high enough when Earth was forming that we actually volatilized a little bit of silicon, right? That gives us some constraints on the thermal conditions. And then as we move down, we find elements more and more depleted from this kind of what we call bulk chondritic Earth model. So I see we've kind of reached the end here. There was a bunch of stuff I wanted to talk about, which I didn't get to. So I'll add it to our next class session, which will not be in session. We're not meeting on Tuesday. And on Thursday, I will be on an airplane. So I'm going to be giving you a video, asynchronous video that you can watch whenever you want. So it'll be the next topic plus the last few things in this presentation. Any questions?